I'm going to talk about some of the details about running dyno tests. A lot of this stuff applies both to inertia, chassis, engine, all sorts of dynos. One of the things, anytime we do dyno testing, is we correct the data to certain standard conditions. And the program gives you, oop, over here, three options. A standard race dyno, which has been used for years, so Superflow and DPAC and everybody uses. And the one reason they do is because it corrects it to very good air, so you almost always get the best numbers with this correction factor, the highest numbers. What the SAE, Society of Automotive Engineers, uses, this is for production vehicles, and this does not rate things in as good a air. You can see the barometer is lower and the temperature is hotter, and this actually will produce numbers that are about 4.5% lower than the race dyno. And then we have DIN, which is in between the two, and that's used by in Europe a lot. So anyway, so if we have the standard race dyno here, and these are the weather conditions that are being used, I'm going to save this test, and you can see me doing this a lot. I'm going to save this to a new name, and I'm going to go in now and change the correction factor to this one. And this also illustrates the point that with everything I'm doing here is it illustrates the point that you can fix problems after the fact. That, and with a lot of dynos, you make a pull. If it isn't perfect when you make the pull, you're out of luck. You cannot fix things. But I have now made that change. I'm going to graph this now. And I'm going to, here's what we call a history log. This is another way to have overlay graphs. You can see in previous movies, I would use this add test thing. But I'm going to use the history log now because this is a little bit more advanced, a little bit more easy. And whatever you click on graph in this graph column, I put a yes there, is going to be included on the graph on the screen. I'm going to click here, graph test mark yes. What we have here, I'm going to turn the fuel flow off here because the fuel flow is identical for both of them. And it just makes it a little confusing. Here you have your power curves, and you can see the one marked SAE over here is the low one. I'm going to format legends. I'm going to increase the legend size here a bit so we can see things a bit better here. But here you can see the horsepower for the SAE is 393, but it's 411 if we use the race dyno. And I think most dyno operators realize that the higher the numbers, the more happy the customers. It's a perception thing. But that is one effect that you have to pay attention when you're comparing dyno data. Another thing is we're doing accelerating tests here. And when you are accelerating an engine, some of the power the engine's producing goes into accelerating the engine's inertia, the crank, the pistons, rods, the flywheel, the dyno itself. And that, depending on the acceleration rate, can absorb a fair amount of power. And if we look here, let's do a graph here. Let's do our time graph like we've done before. Let's just do the power run. And we do, here's the acceleration rate. And you can say, oh, this is a very slow test. Yep. I'm going to pull out a test that's got a faster acceleration rate. Here's one of our example tests. This is the 4.6 liter V8. And you can see it takes 20 some seconds to do the whole run, but from here to here, it only takes about 5 seconds to go from 3,600 up to 6,000 RPM. So a fairly high acceleration rate through that part of the curve. And this should be producing less power than if you had a slower axle during that part of the curve. Now, what the program gives you the ability to do, if you go into preferences, we kind of hide this because if you're not careful with what you're doing, you can actually make your data less repeatable. But here, absorber dyno, allow correcting for engine inertia effect. That's turned off. We want it, that's the default condition because unless you're careful, and it's a warning you here, unless you're careful, you can introduce more errors in your data than you're fixing. And this is only available in the pro version of the software. But what we're going to do now is now we have this ability correct for engine inertia effects here. And we can turn that to yes or no. So having that preference turned off, it would be the same as turning this to no now also. But if I say yes, what I'm going to do here is I'm going to save this to a new name. Inertia. And what determines the amount of inertia in the engine are these settings here. Basically, what size engine you got, and we have to make some approximations from that, and a crank weight, and how many pounds, and this is some description. We don't use that for anything, that's just for your notes. And a flywheel weight and diameter. I'm sorry, the flywheel weight should have been more like 15. And 12-inch diameter. Crank weight is probably more like 45 pounds, let's say. We back out of here. I should show you. Everything illustrated in blue here, like it says, are being used to estimate what the total engine and dyno inertia is. Okay? Now, if we do a graph of what we got here, and we compare to where we started, this one here, you can see the difference, especially up here at the top end. At the lower end, where the accelerate was slower, there's not as much difference. But up here at the top, where the accelerate got to be quite high, you can see 263 versus 269 almost. 396 horsepower difference when you account for the inertia. And when you're accounting for the inertia, you do get a higher number. And this is an honest change. We're not faking things out. You should have more power if you're accelerating, and you account for the inertia effects. Another thing that can affect results is temperature. For example, we do a correction factor, and you can either type the numbers in yourself, or like in this test, it was recorded by a weather station. Well, let's say we wanted to see what would happen if the temperatures change. I'm going to go and temporarily, I'm going to turn off the weather channels, and that's going to give me the ability to change this. And now with the weather station turned off, I can go over here and look at and make this change. The weather station records everything the same as uncorrected barometer with dew point. And these numbers will stay the same. Now let's say what would happen if the temperature was actually 80 degrees instead of that 66 that was there. You can see it changed the density, altitude, and stuff. What would that, what was that, a 14-degree change in temperature look like? I'm going to graph it here, and here's the difference. And you can see 68 versus 73, or 69 versus 73, about a 4 horsepower change from 14 degrees of temperature change. What that means is if the temperature is in error, the temperature you're reading, air temperature, is in error by 14 degrees, you're off 4 horsepower for this case, which is looks like about 2%. One thing that can make the air temperature off is a little discussion on weather is if you use our internal weather station, the temperature at the box, which is actually inside the box, there's a circulating fan to make it fast responding, but it can be different than what's over at the engine. You might have exhaust heat, all sorts of things could be different over at the engine. And the temperatures could be significantly different. So it is definitely more accurate to actually measure the temperature over at the engine. And how you would do that is you'd go over here in your DataMite specs, and one of these thermocouples you could turn on, and thermocouple engine intake air temp, and you would see this if we were doing it. If you had purchased a thermocouple, an engine intake air temp thermocouple, you would actually see this some paperwork that talks about this. But that will actually make things a little more accurate. The barometer at the box and the DataMite are the I'm sorry, and the engine are the same. The barometer is exactly the same. The humidity is, for all intents and purposes, almost identical at the box, the DataMite, and the engine. But the temperature can be significantly different. And so that's one thing to improve your correction factors, to have a separate air temp thermocouple over at your engine. Other things that can affect test-to-test repeatability is just engine temperature. If you start one test at 200 degrees and another test at 220 degrees, you are going to get different temperatures. Or that could have been oil temp, it could be water temp, it could be head temp on an air-cooled engine. So you always want to start your test at the same temperatures. Another thing is how you run the test, how you accelerate or control that engine during the accelerating or decelerating part of your absorber dyno test. With an inertia dyno, that is something that you can forget about because the control is so consistent. But with a water brake or an eddy current or type dyno, you do have to control things fairly similarly. Correcting for engine inertia effects will help, but it is not perfect. Same as temperature corrections or weather corrections in general. Weather corrections are better than nothing, but they are not perfect. So if you need critical comparisons like this cam versus this cam, don't run this cam today and cam B a week from today. Try and get them all on the same day, and ideally, if it's a critical comparison, you want to run cam A, cam B, and go back to cam A, and ideally go back to cam B, because just pulling the engine apart and putting it back together can change things. I've seen it when I worked at Ford Dyno. We had everything in very controlled conditions. You pull an engine apart and put it back together, and it can be slightly different. So you want to make sure when it's a critical comparison that you do several tests, check for repeatability, and go back and forth between the modifications. And I know with a CAM that's difficult to do, but if you need the answer, it is the only way to make sure. Another thing that can affect the data, especially if you like to look at torque and horsepower peak numbers, peak torque and horsepower numbers, which I don't like to do myself, but a lot of people do, is what kind of filtering and what kind of RPM step increments are you looking at? For example, here we have a fairly peaky engine. This is a two-stroke. And if I click over here on this horsepower curve, here's the peak. I click, that's a little feature in the program. You can click on a point and it's showing up over here. On the main screen here, we got 16.96 peak horsepower at 10,200 RPM. And this is being a certain amount of filtering, and it's done in 200 RPM increments. If I go click on a graph, make a graph of this thing with no filtering, and I go look at the peak, I'm getting 17.13, 17.14. I'm getting more peak torque and horsepower because of the jumpiness of what's being shown on the graph here. And that's because the graph will show things in great amount of detail. We're doing things in 50 RPM increments. If you see here, if I move the cursor down here, I'm at 10,050, I'm at 10,000, I'm at 9950. Things are displayed here in 50 RPM step increments. And that's why you're going to get a higher number here, because it's going to look at this stuff in more detail. Now, just filtering. Put some filtering on this, and it was 17.14 was the peak, and now we're down here more like what was on the main screen. 16.83 appears to be the peak. If we look over here, if I put on heavy filtering, I can knock that down even more. But when I'm knocking down the peak, I'm also filling in the trough here at the bottom. Now, there's no easy way for me to do a comparison of this on this screen because everything's done at the filtering level that you specify here. And we do that on purpose, so you don't take one test with no filtering and compare it to another test with lots of filtering and say, boy, look at the difference. We keep the filtering the same. So anyway, now you say, well, I don't like that. I want to make sure that every point of the program is matching. I don't want a peak torque here of 16.96 and anywhere from 16.5 to 17 on my graph. Well, we have an answer for that. If you go over here and click on the Calculations Continue tab, I guess it's Calculations tab. I'm sorry, it's the Graphing tab here. Specs for RPM graphs and reports. You have two choices. The user sets the increments and filtering, and that'd be 50 RPM in the graphs, or The increments and filtering match the main screen. This means that done on a report, done on a graph, or on the main screen, everything will match. And when you do this, now what you have on the main screen, like this main screen RPM increments of 200 and main screen filtering level, this will now be applied to everything else in the program. So let's make that change. And you can see here, if we click on this, we didn't change what happened on the main screen, but when we go and click on the graph screen, you see the filtering was not even allowed. If we click on this, the filtering is not even allowed to specify because the program will determine what that is. And we go click on the graph here, we got the 16.96. So, and if we go in steps now, you can see we're going down here, we're going in 200 step RPM step increments. And that might make things a little more clear and easy to understand if you want to go that way. But a lot of people like having the more detail in the graph. So it's a personal preference. But that should give you some things to think about when you're trying to do comparisons and trying to figure out why one test may not match like you would expect it to another test.